My name is Nikolay Vizovitin. I work at this company. We make hosting platforms, and I will have examples from time to time related to our product. I think you'll have good view. You'll have a good view. Some technical problems. Free software has a principle. It allows you to study the program and adapt it. That's the concept of the open source free software. So it relates both to the source code, but also to the executable code. So the first thing can be studied by a human and checked, but the second part is used by the machine for practice purposes. However, there are some nuances. So the first is transformed into the second through some assembly function. It's one-way function. You can assemble the source code and get the binary, but the reverse is either not possible or very complicated. It results in such thing as that you cannot be sure by having a binary code that it was assembled from the given source code unless this build function is determined. A couple of concepts to start with. To the left, we will have reproducible things, in simple words, that anyone can reproduce this transaction. To the right, we have the concept named repeatable. Again, it means that if the transaction is repeated, the results are identical. What's the difference between the two? Reproducible, we guarantee that input data and the performance environments is the same. However, in repeatable, we fix the source data and some important features of the execution environment. You will see later in my presentation that reproducibility is a possible solution between the source code and the binary code. But why it is a problem in the first head, and why it is important to resolve it? CIS conference in 2012 had some CIA conference had some leaks. And there were some unnamed researchers who claimed to have created the malware, and in fact it was the SDK, software development kit. It's like patchwork compiler, and it allowed them to do some bad things, to mark binary files and to build into these binaries codes for sending back some data, to inbuilt trojans into binaries. Moreover, over several months after publishing this information, in fact, in Wild Nature, some modified Xcode versions were identified. So the solution is to have reproducible assemblies. If you can guarantee that by using the same source data, input data, you may get the same binary artifact, then you may claim that several different people can assemble the same source code and make sure that the results, the outcomes are identical, verifying that the determined binary artifacts correspond to the source code. And there are many great projects which support this initiative this way or other way. It all started with Concord project, because they started developing this issue in 2012, dealing with money. Then Total Project followed, because they care about human life. And then it was supported by Debian community and other projects. Debian distributive is, by 93%, is reproducible. Now back to my presentation. I will tell you how reproducibility is applicable to arithmetic operations, to creating utilities, to assembly, and I will finish with package assembly, and we'll talk about long-term utilities and assemblies which support them. Arithmetic transactions. I'll start with them. Their main purpose, including quotation marks and dot semicolon, to be accurate and to keep high speed. Very often these two concepts are opposite to each other. So look at this slide, you think everything is true? Unfortunately not. This slide gives you an example how the same transaction of dividing by round numbers can be realized using cat3 and Python. And you see, in different environments, you can get different results realized through different mechanisms. This is an example that a simple divisibility transaction cannot be sometimes reproducible when the environment is changed. Then, associativity transaction with the floating point. It's well known that such transactions are not associative. Well, it's not that bad if unassociativity is achieved by automatic association. Here, and you see plus operation and multiplication operation are not associative. Let us turn to commutativity. The standard says everything is fine. In IEEE 754 says it's warranted. We may say that this equation is true. Not quite so. Look at the example at page 13. So here we check whether two identical equations x plus 1, whether the result is identical. And in some architectures with some compilation flags, we will get that these two statements are not equal. This is due to the super accuracy in the mathematical process, but this is the fact that it could happen. Mathematical functions. It depends on the implementation type with different accuracy. And there is no official standard to dictate the standard accuracy and how to round up the outcomes. Moreover, from the mathematics standpoint, for the majority of functions, this task is not resolved. If we say we have a limited operational time, how is it relevant? First, client-server architectures and applications, where you have to do calculations of the same thing at different servers than for game development, for multiplayer and replay, and for some tools. Of course, for assembly transaction, you will not floating commas, floating points. However, my recommendations: always test everything you rely on. Use compiler options to afford this balance between reproducibility, accuracy, and performance. You may consider figures with fixed point or other mathematical concepts. My next topic in the presentation is creating tools. I will go quickly through this. Essence: avoid using global state. Avoid using true randomness. Prefer using pure functions. Use deterministic algorithms without so-called side effects. Most of the algorithms, in fact, are like this. And the most important, test reproducibility. All the rest is outside the discussion. So everything which I listed is applicable to the development of utilities and algorithms. Let us talk about reproducible builds. So a build is reproducible if given the same source code, relevant attributes of built environment, and build instructions, anyone can recreate bit by bit identical copies of all specified artifacts. Reproducible builds. As a practice for software development, can create a verifiable path from human-readable source code to the binary code used by computers. There are some advantages of this practice of software development. So we already looked into resistance to attacks for developers and for developer machines. For many attacks of this type, having reproducible builds is the only way for early detection. The other thing, if your build is reproducible, your binary artifacts will have more similarity with small differences in the source code. On one hand, your binary patches are smaller, shorter if you use them, and it is easier for you to test refactoring and changing in the build system. Changes in the build system. Also, to assure quality, when you regularly test reproducibility, you would identify specific build-related issues. At the same time, you would save on testing of similar binary artifacts. Example, if for your product you update and release updates regularly, and your cycle has a certain pattern, by binary artifacts you can identify the functional elements of the product affected, then you significantly save on your testing effort. For example, in my company, our product is not monolithic. It has a number of files, quite a big number of files. So we support many configurations. I think 8 for Linux, 11 for Linux, 8 for Windows, and a couple of years ago we have 25 configurations for Linux. And we need to release updates weekly on average. So the total regression, if we start it in one stream, will take several days. Several days. considering that through analyzing update, we may identify the affected elements in the product, we can significantly reduce our testing effort by assuming that we have good unaffected parts. It will also increase the speed of your development process. Less rebuilding is needed, less build time is needed, because you can aggressively cache intermediate artifacts through the repeatability. Excuse me, reproducibility. Only 3% of developments are, in fact, unique. That's what Facebook tells us. And in my company at Plesk, we save a lot by using this mechanism. Reproducible build is documented. Once documented, it allows you to have effective reviews of the build system, may identify bad or corrupted input data for some build rules. If at a certain library version there was a vulnerability, you can easily understand whether you use this version and plan its upgrade. Also, if your build is reproducible, it is easier to comply with licenses which require to provide the source code. Because it is easy to identify versions, dependencies, and the source code related to them. However, pay attention for all these items except for the first one. In fact, repeatable build will be enough, but the first one requires the reproducible build. What's the general approach to have this practice of reproducible builds? First, you have a deterministic build system. Then, you have to identify important aspects of your built environment and to distribute the built environment for other users who would build your product. And to make sure that the users get the same result, they must have a certain comparison protocol, and you provide it. Let us start with the first point of making your build system deterministic and to afford reproducible builds. Say, what are the main sources of non-determinism? Unstable ordering of inputs and outputs, then use of volatile global state, and true randomness. What shall be determined at the build? Well, it is determined by the limits of your build environment. However, in general, main key steps are the same as it was already detailed in the first slide. Let us go to further details. You can have a small file. Using mask, we have some files. This make file is not reproducible. To make it reproducible, you have to either list explicitly the source files or sort them out. You have to take note of the local.
Here is an example of archiving. The system may provide you files in different order, and it depends on different reasons. So it's important to sort it out. Even this is not sufficient. You have to sort them in a fixed manner, or to obviously point at all the features. Next, stable order for exiting. In many languages, there's the data structure in the shape of languages, hashes, associative massives, and as a rule, there's protection from attacks. And at a reiteration of this structure, the keys may be given to you in a random order, so they need to be sorted. The other option is to retune the system, reset the system, and to have the initial values for the relevant algorithms. And of course, you have to consider the local. The access to the modified global condition, global state. That's the kind of different kinds of limitations, like sandbox build process, the resetting of a global state to the initial, or the exit of that global state into the obvious inputs of your assemblage procedures. Next, volatile inputs. Different artifacts are meant that may get modified or disappear. Usually these are inputs from the network. A good example of this situation is the left pad package that disappeared from NPM repository, and many developers have had a headache. What solutions are possible? You may not rely at these input data, or you may check their integrity and keep somewhere the backups. Text information on the versions. You needn't generate the numbers of the versions with each assemblage. Make the information about the OS determined. Also, the current data and incremental ID is not very useful, in fact, especially if your assemblage is repeatable. How can you get around it? Build ID may be a hash of the source code, and version information could be extracted from sources. It may be recorded, it may be taken from the changelog entry, etc. Next, timestamps. It's better to avoid them at assemblage. Mean not to include them into the resulting binary artifacts, or they may be based on certain fixed database changelog information, etc. What solutions are available for bringing in the necessary stamp into all the assemblage places? You may start it, the fake time utility, or you, I'll later tell it some drawbacks, or you can implement source date epoch and realize the fixed stamp that may be used. Maybe utilities support it, or you may use a certain post-processing to remove or normalize timestamps. Locals. If possible, better to explicitly set the LC all. And mind you that different parts of a locale influence different processes during the assemblage. Here is an innocent example. A C locale was replaced with ENUS UTF-8, thus the sorting order has changed. Many archive formats include, in the result of their work, different details about the environment, like time of modification, the file ordering, users groups, identifiers, permissions, GIDs, etc. Most of them have options to make output stable, But if it's not applicable for certain reason, then the relevant modifications may be done via post-processing. Next, build paths up to the source files. Sometimes there are many compiles included into debug info, and therefore, for example, GCC does it this way, and build ID, which is recorded into the binary file, is based on this information. It means on the assemblage ways, paths as well. So if you have different paths, and then the info is given with the help of the strip program from the binary, then you'll have a different binary files since they will have different build ID. What's to be done? You may use the options of the relevant tools or to use the post-processing. Randomness, random values. For the generator of pseudo-random numbers, you have to have a fixed value. And for most of the tools, it may be done with the help of certain options or environment variables. For example, for GCC, during the assemblage, for optimization during the GCC generates random suffixes. On this slide, you see certain sources of random numbers. Next, the value initialization. One should get convinced that all the values are initialized and you are not recording anywhere the non-licensed memory blocks. That's regarding the languages that do have such a problem. Please use tools that are relevant, like Valgrind. On this screenshot, you can see the comparison of two results of assemblage of Coreboot. The problem was detected with the help of this comparison. Next, stable dependencies. All dependencies should be fixed to a specific version. This may be done with either with a package manager for your favorite language or via vendoring. Hence, that is done as follows. You commit, in fact, all your dependencies. You check them in, or you store them somewhere in the file system. It should be mentioned that one should test the reproducibility. For example, PHP Composer generates each time the randomized autoloader. This may be switched off with the help of the configuration option. Now briefly about the assemblage tools. First, some tools will help you achieve reproducibility. If possible, you may use them. If impossible, you may use them in practice as described earlier for your current assemblage system. The first is TUP, top. Not well-known assemblage system, but if in principle you are interested in assemblage systems, I do recommend you to consider it. It's a very small, simple system with certain interesting ideas. As for reproducibility, it uses Fuse for isolating and monitoring of dependencies, and it limits the monitoring of environment variables. Next, Basil does a lot of assemblage steps in a certain sandbox, and it prevents the usage of such determinations, time, date, etc. In some cases, it rewrites source paths in built objects, normalizes the outputs if necessary, controls environment variables, and in general does a lot to make assemblage reproducible. In particular, does everything to prevent the usage of global dependencies during compilation. And it's heavily focused on Google's way of doing things within Google. Whether it's good or bad, it's up to you. For example, in comparison with the back assemblage system by Facebook in Basil, you can't make anyway the dependence on the library, which is globally installed in the system. This may be unusual and maybe in the way that depends on your project. In this regard, Bach is more flexible. As for all the rest, it does pretty much the same. Next, pants. It's also a build system similar to Basil. It's used in Twitter and some other companies. It supports less languages and technologies, but in general, it's pretty similar regarding its properties. One more thing, another system similar to Basil, it's called Plesk. It's also different from the point of view of certain parameters. And the last one is called Maison. It's an assemblage system which is the front end for Ninja Visual Studio and or Xcode. It has no wildcard support for sources, source files, and it's used by projects like systemd, Streamer, some projects from GNOME, and some others. How to choose the relevant assemblage system? If you have certain experience of working with auto tools, check out Maison. You will like it if you have background of auto tools. If you are used to make files without any generators like auto tools to make, etc., try TAP. It's like make but with steroids. Do take a look at Basil. It has several very interesting ideas. If Basil seems too limiting, try Bach. Too restrictive. If you're not a fan of Java in a build tool, try Pants or Plesk. Next, how to determine what is part of your build environment and how it should be disseminated. This is a list of certain standard parts of the build system. To determine the build environment, you may say that it must be built from the source code. You may say that it's a kind of a fixed distribution with a set of packages and their versions. You may say that you have a virtual machine or container. It may be used as a build system. You say it should be assembled from the source. You may use external resources. That's what the core boot does. Consider recommendations for different remote files. You may check in everything and include everything. That's the approach in BSD and Basil. You may deliver or ship the toolchain as a build product. That's what the OpenWRT does. And this build product should be reproducible. It should have this property. Next, if you say that your build environment is a kind of a distributive, you may use a certain stable distribution, record the package versions, and somehow make sure that the necessary package versions are accessible. This is what is used by Bitcoin and by the Tor project. If you want to distribute the build environment as a VM or container, you may use such products. Other options are available as well, but these are the most popular one. Gideon is a project which was initially developed within the Bitcoin project, and later Tor project used it as well. It runs bins using LXC or KVM, LXC, and it works on the basis of certain descriptors. Next. Everybody knows about the Docker, so I won't describe it. One should mention that Basil, for example, has support for building Docker images reproducibly. With Docker and VMs, there is a similar problem. If you provide some pre-built artifact, then where's the guarantee that it has no bugs in it? This may be important. Vagrant. I guess many heard about it. Its benefits, it may be used with Windows and MacOS. Next, how to check, to verify the reproducibility. You should provide the direct comparison of cryptographic checksums. The protocol use either direct comparison or cryptographic checksums if the artifacts have certain signatures. They have either to be ignored or excluded from the artifacts before the comparison, and it's a must to verify your build at certain modifications, variations. The algorithm is simple. You build twice with different build environment and compare the results. Next. Tools that may be useful. Strip non-determinism normalizes different archive file formats, and it's extensible. It makes files orderly, normalizes the time marks, etc. Disorder FS, useful utilities that may overlays fuse file system that introduces non-determinism into FS metadata. It works via fuse. Next, a diffoscope. De facto, it's a deep recursive diff. You may go here and try it. Browser, very simple. Provides a complete report either in the shape of a text or HTML. Fake time. With the help of LD preload, it makes the daughter processes believe that time goes in a different way. Of course, it may cause certain problems with build tools that rely on certain properties of this time. It may cause problems with make, for example. Reproducible. That's for executed files on Windows platform. On Windows platform, the executed files are always non-reproducible because they include the time marks. And these utilities enable to post-process them to make them reproducible.
Packaging. There are two parts into packaging. First, to build what you package in a reproducible way and then package it reproducibly. For DEP packages, we have pbuilder utility, which launch the process, then call builder above it, and a bit obsolete as built. In fact, they are archives, and you can recess them to afford this determinism. With RFM, the post-processing, it's a bit difficult, more difficult. However, there is the requisite called mock. It will help you. My final thoughts. Let us come back to the initial slide with terminology. You have to distinguish between reproducibility and repeatability, or what is named sometimes as stability. Reproducibility. Say, when you have reproducibility, you may change the environment. Do you need reproducibility? If you work on a closed source, then probably not. But if you achieve repeatability and reliability of your build, you would get many advantages. On top of that, if you achieve reproducibility, you'll pay more. You invest more effort. Reproducibility requires constant testing, continuous testing, and you need rebuilders. So those people who will ensure the trust web, uploading your source code, build it, and confirm that what you built and put it on your website, in fact, is identical to the source code. My next slide repeats the slide from the beginning, except for the security element. These are your advantages. Of course, it requires some extra effort, but if it is achieved if you have repeatable builds. So your quality is assured, it's good, your development speed is higher. Now, what we do at Plesk. Our project mostly have closed source, so we do not want to get to reproducibility. We focus more on repeatability of our builds. We have many configurations, a lot of them, and we shall test our products on them, and we shall build our products for them. We also have quite a lot of languages and technologies in use. So we decided, we also made a decision to switch from make-like system to buck because of what I listed above. And so far, we are satisfied with this choice. What can you do when you get back home from this presentation? Take your project and try to build it twice in a different environment or in the same environment. And just compare whether the resulting binary artifacts are identical. And just compare them using the utility of this default scope. And you may find diffoscope, you use decafoscope, and you may find some interesting results. Reproducible builds, it's spearheaded by Debian community, includes numerous other projects. It's a good starting point. If you want to use the practices described by me in my presentation, it also offers a service for continuous testing of builds reproducibility. And moreover, if you have an open source project, you can write a helper script, a small one, and submit it to the system, and then your project will be tested continuously for reproducibility. Thank you. I am here to answer your questions. My question, can you give more details whether it's in fact, when you have reputable builds, whether it's indeed simplifies your development? And my second question, you test only those parts which are binary tested, but let's say one ISO's corrupted an unchanged binary. Say, and what's the advantages against like CC cache? Okay, first let me answer the second question. we had a project where Ccache was used. There were minimal changes on the developer side, and then rebuild would take about 3 minutes. Considering that cache was still warm, once the new build system was introduced with the minimal changes, the rebuild takes about 10 seconds. You may ask why. It is related to a number of factors. Ccache is quite a simple tool and easily implemented. To use Ccache, you need still recall the compilation of the same files. Using repeatable builds, you can cache other artifacts like static libraries. You may cache static libraries, some object files, and if there are changes just in one implementation file, in fact only one object file is changed, and you built one changed static library and get the binary. All questions please into the microphone. But in fact, you explain what main time does. Make use PM time, correct. You worked with make, right? So you understand that. Using make sometimes is a headache because checks against main time are not always stable. I'm not telling you that implementing repeatable builds is a magic tool. It's one of software tools helping you to improve your development in some aspects, and in combination with some extra additional efforts, it may give a significant advantage. So the main aim of reproducible builds is to solve security issues and trust issues for those who provide binary artifacts. So this is the main challenge resolved by reproducible builds. Thank you for your presentation. Binary reproducibility is good. I do not quite understand, though, why Plesk vendor needs reproducible build, because you provide customer the distributive and you are responsible for it not being infected, because we have, for example, in cross platforms, we will be more interested that the functions stay intact. We are not so much interested that, let's say, in binary a hash was changed. The answer. Functionality stays the same. It's an advantage. Moreover, if you can use cross-compilation and check that in cross-compilation your builds are reproducible, you may save your resources at a more powerful machine. But let me reiterate that repeatability of binary builds, it is needed for caching of the build results. I'm partially answering the first question, by the way, at the same time. So, and also, we needed to save resources of those who test our products. who test products, because the full regression is quite lengthy, and our products are constructed in a way. It includes quite a number of somewhat independent utilities, plus some script files. Looking at the changes of binary artifacts in our product, you can see what the changes are in the product. It's not applicable across all the range. However, in such cases, you may limit your test effort to certain fields. And then against of running the full regression for our updates, we test only the elements which were really affected. And it saves a lot of both machine and human resources. What are disadvantages is the question for repeatable builds. Well, the colleagues gave me an interesting insight. A disadvantage, if the difference between the same artifacts, with small changes in the source code is small, then in releasing certain updates to cover security holes, it would help you to understand the nature of the issue. But when we have a project with open source, the approach is that the security is not security, and we shall have the same approach. But that's the point. There could be an issue. And we must approach it based on the process by proving to users to update their versions where all these problems occurred. That's number one. Another issue. If you want to achieve reproducible builds, you have to continuously test it and assign some resources to it. So that's your fee for using the approach. The question is off mic. Unfortunately, we can't interpret it. The answer. Currently, for us, it's yes. But advantages for in-caching of intermediate artifacts are important for us. One more question. Thank you for your presentation. You mentioned that the key challenge resolved by reproducibility is security. My question may sound naive, but how do you solve the egg and chicken problem? How to find the absolutely trustworthy compiler that would build or assemble our source code? To a certain extent, it is resolved by good strapping of the compiler, because it's believed to implement the code into compiler that would allow in compiling this compiler to get the same compiler with malware is quite difficult. So I'm not sure that there are practical examples of such malpractice. While in all other respects, you have to have some basic trust as a departure point. Thank you. Let us thank the speaker.